Presenter is Michael Freitag, our Technical Product Manager for Magnetics. Before we start our webinar, I have some information. We invite you to ask us questions. You can address your questions at any time during the webinar with the chat function on the right-hand side in your browser. We will answer all of your questions at the end of the webinar. Also, no need to take notes. We will publish the presentation afterwards. Hello Michael, thank you for presenting again today. Please tell the audience shortly about your role inside KEMET, and then you can start the presentation.
Hey, good morning, Alex. Good morning, the audience. My name is Michael Freitag, as Alex already told you, and I'm responsible for the magnetics product management in Europe, together with a few colleagues. And so we have some announcements to make, let's say, or some new series that we want to go for. And yeah, let's start. I mean, as Alex said before, we are introducing, let's say, a range of power inductors for buck and boost application, but also if you want to do noise filtering in differential mode ways. So there's always the concern about the power loss, and that's what I will talk about today. Okay, for power inductor for boost and buck and boost applications, or EMI, I mean, we mean usually a lower voltage range of up to 48 volts because of the insulation of the component as it's connected from lead to lead by metal composite material. It can only withstand the lower voltage range. And actually, the core losses, as I said at the beginning, play a major role in the component behavior and in the efficiency of your whole circuit. As with higher resistance, of course, the component will have a higher heat rise and will have more power losses. And we developed a few new materials that increases permeability and therefore reduces also the number of turns. And as a result, it will come back with a lower DC resistance. And you may compare this in the industry. You may compare this with our old series. So it's really a next level of efficiency rise. And so we are coming out in the market with, we have already released in May or June this year, like the smaller case sizes from 5 to 5 to 8 to 8 millimeters. And in October, so next month, there will be an addition of the range of 10 by 10 and 12 to 12 millimeters. And also, probably a month later, there will be the 17 to 17 and 22 by 22 millimeter. In total, we're talking about more than 200 part numbers that we will release. And I will tell you how we came to this. But first of all, let me give you a brief overview about KEMET. And more or less, I would focus more on the token section, because what we're doing here with magnetics is not a resale of other suppliers, but it's actually our own product range that was developed by the Token Corporation that KEMET took over in 2017 completely, and it's now a full member of the KEMET family. And when you look at the right upper corner, the 16,000 employees, 5,000 of those are coming from the former Token Corporation. So we are present everywhere, and we have also the possibility now, not limited to, let's say, the Japan and Korea area where we have been predominantly active before, but now we can also ship to all the countries where KEMET has representatives, and specifically in Europe and Central Europe, we have good possibilities as we have a wide range of customers that we can touch. But before we start really with a new series, I want to give you an idea about what are the differences in magnetic core materials. Because what we always say also at customers is that everybody can put wires around something. That's not really tricky, but really the magnetic material is the main dominant feature of a magnetic component, of course. So the magnetic core materials are developed for different applications, and there are some main material criteria, not to say that the others are irrelevant, but for some applications, we're focusing on the core magnetic capabilities. First of all, there's magnetic saturation, and this describes how much current and how much magnetic field you can store basically in a component. And the magnetic saturation says at which point of current there is not any more magnetic energy that we can store in a component. And the result that you can see, and you see this also from the datasheet graphs, is decreasing inductance. So that means with higher DC currents, which lead to the saturation point, you will see a decreasing inductance. The other one is a thermal core loss, and this is when you have an alternating electric field which introduces an alternating flux in the component, where the direction of the magnetic flux is constantly changing. That creates some losses which also result in a temperature rise against the thermal resistance, of course. I mean, we have a power loss, and the power loss is connected to the thermal the thermal resistance, and based on this, it will cool off a little bit. But I mean, usually it heats up the component. Then the other one is the frequency behavior. It is maybe also important here, but it's more for EMI solutions, and there's a few materials that were specifically developed for certain applications. And we have also a permeability, and the permeability describes how easy you can steer a magnetic field, or how easy you can change the domains in magnetic direction towards and from the outside connected field. So the permeability influences the mechanical side, because the higher the permeability is, the less turns you need basically to create an inductance. So the first two parts are more relevant for power applications, and the second two main aspects are more connected to EMC. What are the losses in detail now with, let's say, filtering? If we have an EMI application and we only are concerned about immunity and emitting of let's say, high frequency noise or interferences, then basically all in all, the temperature rise or the power rise of the components is connected to the copper loss, which is I squared multiplied with the DC resistance. So, and this is basically also for all the other applications a main parameter. But when you use it in buck or boost current smoothing applications, then the total loss is the core loss plus the copper loss. So the copper loss is always there, of course, when you have a high current, but the core loss comes in addition. And the core loss, as I explained on the last slide, is related to changing the magnetic field or changing the magnetic flux direction, better to say, constantly and alternating within a pulsed application. And the core losses depend on the voltage difference between the in and out of a switch mode power supply, and also of the switching frequency. So the target, of course, is to reduce all the losses to increase efficiency overall. Because when you consider that the rated current is measured always at 40 degrees C heat rise, then you also know that there's a lot of heat introduced in the circuit if the design was not made right. There are additional losses due to winding structure. There are AC losses. There's the winding shape. You can do flat windings that have a better high frequency behavior. You can do round ones, which is standard and also the most cost effective. And there's also leads wire, which we usually don't use, but if there's really high frequency involved, it could be a thing going forward as well. There's a proximity effect and eddy currents, but the copper and the core loss, they remain the highest of all in the usual applications that you're using this, for instance, for EMI or for buck and boost applications. So we have a tool on the ec.kemet.com homepage, which is our engineering center, and there is a tool called Inductor Core Loss Calculator. So the link you can straight take from the presentation, otherwise look for tools on ec.kemet.com and you will find it straight. And I've taken some data from the last, let's say, power inductor series that we made with very similar material, because our latest series is not yet uploaded, but we're working very quickly to get this done as well within the next 1 or 2 months. In an EMI application with DC, for instance, if we have a component, in this case it's 1.5 microhenry, and it's in a shape of 6 by 6 millimeters and 3 millimeter high, we have, for instance, a DC resistance of 10.8 milliohm, which create a power loss of 1.08 watt. And at losses, when you drive this component with around 10 amps. So the heat rise of the component is 47.3 degrees C. So you really need to see if you are below the specified temperature. And in this case, the MPLCG was only rated 125 degrees C. So the old series might not be capable for your application. In addition, when you now use it for buck or boost, then you see that with this calculator you can calculate an additional AC copper losses, which is a little bit, it's not too much, is 0.026 watt, so really not so much. And then you have the core losses here in this case with 5 volt input voltage and 3.3 volt output voltage at 300 kilohertz, which is roughly 0.05 watt as well. So what I said before, the main losses is really related to the DC resistance, and the others are adding up in usual application. Of course, if you have a very different application, let's say you are coming from, just to say an example, from 48 volts and you want to go straight down to 3.3 volts in a buck converter, I mean, that is then a very high voltage level to overcome, and you will see much higher heat rises. But in usual applications, as I said, it's relatively limited when you use these, and the DC resistance is really penetrating most to the losses. When we now compare the old MPLCG series to the new MPX1D series, which, by the way, the MPX series, all components which are available are 155 degrees C rated from the maximum temperature. And but as I said as well, it's a similar material. But you can see that we have been able, in the same case size, in the first line or first 2 lines, you see the maximum DC resistance. We have decreased in the first case from 15 to 12.7. And in the second case from 41 to 36.7 milliohms, which means that the rated current has increased in the first case by roughly half an amp, and in the second case by 0.7 amps. So it's really an improvement in, let's say, performance in the same chip size, having in mind that this part is also approved or qualified for 155 degrees C. So the improved material offers slightly better permeability, so there's maybe less turns needed depending on the design, and the saturation capability also, what I haven't said before, is linked somehow to the rated current, because if a certain material rises in heat, then automatically the saturation capabilities come down. So that means the cooler the part, the higher the saturation will be as well. When we look at the materials in use today, I haven't compared this with like the very old material. We have a series called MPC, which is not recommended for new designs anymore. But since a few years, we have this Centix 2 material, which is used in MPLCG and the new MPX series. And there's also a path forward to a new material called nanomet. And you will see from next year onwards some series that we will introduce. This is this very new material. And here on this graph, you see that on the y-axis, you have the PCV, which means it's a power loss on the given square, on the given mechanical size. And on the x-axis, you have the frequency. So also with frequency, the power loss would increase. And in both behaviors, nanomet and also Centix is better than, let's say, a standard material. So a permeability The material that we use assigns, of course, the permeability, because we have a number of turns we need to turn around inside, let's say the magnetic material. So if we can do less, it influences the RDC, and also the magnetic saturation, as I said before, is linked to this, and the core losses with the flux direction within the material. So core losses will play a more significant role as switching frequencies are increasing. So if you're working with solutions in gallium nitride or silicon carbide, you will probably switch at higher frequencies, probably in an area above 1 megahertz in low power applications, and in high power applications maybe with a few hundred kilohertz. But in this case, definitely we are prepared for the next level of semiconductors as we brought out a new material. So the Metcon power inductors, as I said before, minus 55 to 155 degrees C. The part number system is quite easy. So we have the product version 1 because we just released the first shot. And then you can see it's relatively easy to understand by case size. It's a so-called speaking part number, and it's very easy to form this, as you know this for other KEMET components as well. Taking an example in the ceramic area or tantalum area, it's also very easy to understand the individual part numbers. Then the product offering. And here I'm also only giving you an idea about the smaller size components, from 5 to 5 to 8 to 8 millimeters. That is basically the area that we can cover. So in instance, when we take these 10 microhenry as an idea, from let's say from like 3 to 7 amps or something on rated current. But if once we increase, and this will happen next month, and the samples are already, by the way, available also in the bigger case sizes on our high service distribution network, as also by our sales representatives and FAEs in the field, and even inside salespeople can get you samples of these components that you can test them yourself. Nanomet, I talked a little bit at the beginning about this, is a new material, and you can see we have already done or developed a new series, which is just going into mass production next year. The series is called MPHV, which will be the next achievement. And you can see in a comparison here, in this case, with 22 by 22 millimeter in case size, a very big inductor, that we can continuously decrease the DC resistance as we can increase with this continuously the rated current, and also the saturation current, again from that component with Nanomet, will be better than the one we just released. Why Nanomet? Nanomet is a component which we designed with mainly it's an amorphous ion material, an ion silicon material, but we have introduced some nanocrystalline dopants inside. And as you may know, that nanocrystalline material, more known from EMI solutions, have a very high permeability that increases the permeability of this, usually from the, let's say, from the most point amorphous ion, from around 5,000 mu to 10,000 mu. So that means that in this case you really have to wind less than before and create a lower DC resistance. At the same time, we keep the saturation capability, and this is usually by square, or let's say by cubic, and also or by grams, related at 1.7 Tesla roughly. So we don't compromise the saturation capability by increasing the permeability. And this is usually contrary. And let me explain a little bit about this, because if you have in mind that a permeability, a material with a high permeability, you can easily bring the individual magnetic domains in the material into a certain direction with a magnetic flux. That means also that you reach that maximum magnetic, let's say, steering in 0 degree towards the magnetic saturation, the magnetic flux, very easily. On the other hand, if you have a material with a high saturation, then you should not reach this so easily, because you will want to store a lot of energy inside there. And nanomet is basically, let's say, compound material which has both benefits. It has a high permeability, but at the same time a high saturation capability. The other good thing about nanomet is, if you look here on the y-axis, you see basically the power loss at a certain frequency, of course, but basically when you see that an iron silicon component or material purely without any dopants would have something around 30 to 40 watt per kilogram, and nanomet brings this down to something like 5. So that means that the power loss in terms of the switching or the core losses basically will come down with nanomet, but again at the same saturation capability. So that is kind of the good thing. When you look at the table, you see that nanocrystal is usually having a high mu, high permeability, and amorphous, so iron silicon, is low. But the result with the nanomet is that we have a high permeability, and with losses, it's exactly the other way around. Nanocrystal has high losses, and amorphous is small losses. So at the end, we come down with like a very low loss, lambda S in this case, or you can call it a PCV. I mean, whatever you want this. But actually, the component keeps cooler by having also improved the other components of it. Okay, information where to find. So we have the core loss calculator, as said earlier. We have a Metcom introduction video on YouTube where William Mack and Wilma Campioni will show a little bit about the performance of these parts. Then we have a data sheet, of course, and this will be continuously updated when all the other series or the other case sizes will be available. So you can always look at this link. I think it should be the same one, even if the data sheet is enhanced. And then on the ec.kemet.com, we have specifically arranged an area for Metcom. So there you will see probably a lot of blocks, design notes, a product brief, all these kind of things where you can have a look at and where you can find some information that you're looking for in this case. And what are the next milestones for the power inductors? MPLCV, MPCV, these were the series we already introduced like 2 years ago. But it was only 7 part numbers. And you can imagine with a lot of customers, I mean, they don't want to go down the road for customized designs, even if we have the capability from not so high quantity onwards. But it is always like a little bit tricky to do this. And the MPX series is now released in May, which gives you all the standard components, standard values that customers were looking for before. The next is in October, the 10x10 and bigger. Then we have a new release early 2020, which will make all the series technically the same, case sizes the same as automotive grade. We are currently preparing over 200 PPAPs, so that's why it takes a few months more to make this happen. And the MPHCV is then also going to be released next year, and also maybe some additions then in 2021. What else is available in magnetics? So we have common mode chokes, of course. It's a big domain for us in automotive as well as in industrial environments. We have EMI cores for harnesses, for any kind of things. TPI power inductors specifically developed for some server manufacturers, but I would say, I mean, I found already some applications as well where high power and low inductance is wanted, either for EMI or for LLC converters, for instance. Flex suppressor sheets good for high frequency attenuation, manganese zinc ferrite plates, a high demand in wireless power charging nowadays, and also DC high voltage common mode chokes that we offer today. And if you are interested in any of those products, or also the MPX series, or whatever you find on the homepage, don't hesitate to contact us. I will be available, of course, for questions, as well as our FAE team and the salespeople. And I think you will find somebody who knows KEMET quite well in your organization that can forward us the information or get you just in touch with us. And if you're not able to do this, on the last slide here, this is my contact information. Drop me an email. Let me know what you desire to know, and then we can go ahead and see what is happening. Okay, perfect. Alex, I'm done with this. I thank you very much for the opportunity. Do you have anything from the audience on questions?
Yes, Michael, thank you for the presentation. Quite interesting, this new series, and I can see some questions which show that the interest might be very high. So please, if you still have questions, you can enter them still in the chat function, and I will start with some of the most interesting questions. So one question which we received more than one time is, are the Metcom inductors AEC-Q200 qualified?
Yeah, there will be, as I said earlier, but we will need a couple of months more. So I would say probably 6 months. So like in February next year, we should be finished with the AEC-Q200 approval. I mean, we designed the parts, of course, completely to AEC-Q200, but we need to qualify the line against this. And as you know, as a former Japanese supplier, we're very picky on the quality. We don't want to fall into a trap. And that's why we take a few months more until we release this, but this will come early next year.
Okay, thank you. The next question is, do you offer any SPICE-compatible simulation models, including different type of losses?
Not yet 100%. So we are working on this. I know that the group our R&D group in Japan is working on a solution for this. We also wanted to include this into our well-known tool, the KSIM tool, on the ec.kemet.com, but it's actually not so easy to do. The core loss calculator is basically a tool in that direction, and there we will put in the data of the components, of course, that you can simulate. But if somebody has a question about, let's say, the schematics, or let's say the individual kind of capacitance and inductance values and so on from these from the individual part number, I mean, they can drop us an email and we will give them, let's say, the model of that one, and hopefully the person is able to implement this then himself into the SPICE software by the parameters.
Okay, thank you. Then we have the next questions. Do you have also THT Metcom products?
No, we don't go that fast. The reason is basically that we, from the Metcom series, we are focusing really on the board level. And we know that usually the parts next to our products would be SMD parts as well. But we have a similar technology, let's say, for very high power, which is, of course, through-hole. And I wouldn't call it through-hole, I would call it rather screw terminal or something, because these are really huge and as big as a size, like a size of a Coca-Cola can, when you have it in. Yeah, and this, of course, does not fly as SMD anymore, right? But in this case, for the MPX, we're focusing on SMD only.
Okay, and one final question, maybe the most interesting question. Does the MPX series replace competitor items like Vishay IHLP?
Oh, that's a good point, Alex. I mean, we have made this as a drop-in replacement, like the Americans would say, against the IHLP series from Vishay, because we say that they are technically dominant on the market, and we are not want to follow the, let's say, the low price guys. We want to follow the guys which are really the technical leader today, which probably will not be the case anymore next year. But IHLP is replaceable, as well as the individual series of Bonds and Pulse. So everything what is case compatible with IHLP, we can replace with MPX as well.
Okay. So just there was then one final comment regarding the simulation tool, so that it's important that simulation models work in other simulators than your own. So just as a short comment regarding the different simulation possibilities with our products.
Okay.
So customers are really looking forward to have simulation possibilities. For the moment, yes, you are right. We need to have different possibilities to compare. For the moment, I think, and Michael, you will agree, the first step always for a supplier like us, like every other supplier, is to create a component, and the next step is to have simulation models. Vice versa would make no sense to have first simulation and then products, right?
I mean, let's say openly speaking, I mean, maybe we can get this task to one of our marketing persons in the US. I mean, we have, as some of you who are listening now may know, that we have quite a big marketing department, and maybe they can make it happen if we give them the parameters that they can plug it, for instance, into PSpice or into other kind of simulation software. We did this with our capacitors in the past as well. So I see that it's important for customers, and that's a good hint. I mean, I will dig into this and let you know what we can find in the next, let's say, few months.
Okay. So perfect. I think I've seen all the questions. If not, if you have any question more than this, you can see the contact of Michael Freitag. You know maybe your sales or FAE colleagues at KEMET. Please be open. Please join again the next KEMET webinars. And for today, thank you, Michael, for presenting, and thank you for attending to all attendees.
Thank you very much from my side as well, and have a great day.
Okay, goodbye.
Goodbye.